Thanks, Robot. Uh, okay, cool. So let's get started. So we're going to start, and first, Asli is going to tell us a little bit about like where different sets of documentations are, because it might be getting slightly confusing at this point. And then we'll go through the rest of the tutorial document, and I added a little section that we'll start with. Yeah, go for it, Asli.
Okay, so this is the LCOGT SN pipe GitHub repository. You may have been looking here to look at this README. So the README renders here, and I've added a table of contents, which mostly works because it's long. And the first item here is pipeline documentation. And then there's the Docker installation. So most of you followed this Docker installation directions, but I want to take a minute with this pipeline documentation. So this is actually in order written rather than potentially the order you might use it in. The first is this Authoria document that Griffin wrote and some other grad students have modified at LCO. Don't know why it's not loading right now. Actually, I have it up here. I've been using it. So this actually goes through, I think, basically the steps that we're going to go over today of how to do difference imaging. I use it all the time as a reference. It also explains some tricks you might want to do, like if your WCS stage isn't working, you can try this mode astrometry option. So this is like your difference imaging reference. Yeah, I understand that Danielle is working on a new version of this. And so this may be replaced at some point, but this right now is the difference imaging. When I was learning the pipeline, I wanted a manual and one didn't exist. So I wrote up my notes into a manual. So that's here. And this actually lives in the repository. It's a markdown file. But if you click on it here or there, either one, it will take you to this page, which again, the markdown renders, so you can read it on the web. It talks about how to ingest data, how to compare catalogs. It has a cookbook, like this is the quick reduction that I do. This is probably run automatically at LCO when you just look at the quick look pipelines. So this is like the steps that I would do if everything worked perfectly. And then I have a more detailed description of the pipeline and how to call it, and then each of the stages and what the different options are, how you can tell if it worked, like using check quality, check WCS, things like that, and how to fix things that failed. This is definitely like a living document. And if you get help on something and that fixes something for you and you think that should go in this document, please contribute it as a pull request or ask for help on how to do that. That would be super helpful for us. So this goes through, if you want like more detail on the PSF stage or on what's happening at the 0 point stage, this document gives that detail. It also has the Landl catalog creation written out generally, which is what we did for the U-band last time. And then I put some definitions here in terms of what all the different terminology means, because this was stuff that I didn't know. And then the different file types. And this is information that I gleaned from like reading through the pipeline itself. The final thing is that I added a link to the tutorial that Jamie's been doing, and I think we're hoping eventually to put this in Markdown so it can become part of either the manual or the pipeline repository itself. But this, I would say this can be like your go-to place for documentation because you have all the different things. I think that's everything I wanted to say. Jamie, is there anything I missed?
No, that sounds good. I just say that, yeah, in the tutorial, I don't have a lot of the like extra options that are used in each stage. Each stage has many possible things that can allow you to troubleshoot, and so the manual has a lot of those. So if you're doing a reduction and something is not working, I would check in the manual for which extra stages and arguments to check out. Okay, cool. If there aren't any questions about that, I can share my screen. We can start going through the tutorial thing. Okay, so I have added this little subsection about ingesting your own standards because some people were asking about it, and Asley and I thought it'd be a good idea to go through this more carefully. So last week when we dealt with standards, I had given you a tarball of like a few specific observations that were on the right night and at the right telescope, so that you could use those to build your own U-band catalog. In general, you'll have to download them yourself using this LCOGT ingest script. So I'll just talk through how that works in a second. So we're not going to download anything from the LCO archive, but just to demonstrate what it's doing. So let's give this a custom date range. All the if you go to the website, yours probably won't look like this. These are all the proposals that I'm on, but there's a public proposal for standard observations because everyone should have access to those. And we only care about reduced data, and specifically data that have been reduced by the Bonsai pipeline, which is the more recent updated pipeline. And then let's say you only have data at LSC, this is the Chile site, and you only have 1 meter data, so you only care about 1 meter data, and you also only care about downloading U-band standards. So this shows you that there are 8 standard fields for the correct site and filter and nights that you care about. So to deal with those, we're going to download those and then ingest them into the database. We're going to use this lcogt ingest.py script, like I said. So let me move things around and start my pipeline. So I'm going to go to, this is my like LCOSN dir directory, or I guess you don't I guess this doesn't necessarily have to live there, but this is where I have git cloned the repo. Then I'm going to run the docker compose command, and that says that the database is ready for connections. And then I'm going to run the docker exec command. So now I'm inside the pipeline. Cool. I don't think it matters too much where you run this command, but just to be consistent, I'll run it in my data reduction directory. So the script has many options. So I'm going to run it with this -h command just to see what all things there are. So you can run it with a username and password if you're downloading proprietary data from the archive. You need to be on the right proposal, but we're not going to worry about that. You can also specify the site, and the instrument, and the filter, and all that good stuff. So I'm just going to copy the command command that I have here. So this should download those 8 frames that I brought up that you could see on the archive. So I'm downloading from LSC, 1 meter data, U-band data in this date range. And Asley informed me that this end date is exclusive for some mysterious reason. So I guess be aware of that if you're downloading this for real. And then I'm downloading reduced stuff that are standards and that are public.
Yeah, I want to also point out, because this has tripped me up multiple times, in LSC loop -E is epoch. And so you give a single date or a date range there without any dashes between the month and the day and the year. Here it's -S for start and -E for end. And there are dashes. And if you don't include the dashes, it doesn't say your format's wrong. It just doesn't find anything. So those are just 2 syntax inconsistencies to be aware of.
Yeah, thank you for pointing that out. Okay, so that should be downloading and ingesting stuff. Okay, great. So this saves you from having to like download a tar file and then ingest the tar file. This does everything in one step. So if I want to just see those, I can do my LSC loop command and the target, the standard field that I ingested set up here is L94. Okay, and so those U-band observations that I ingested are now in the database, and so now I can like generate PSFs and then use them as standard fields and do all that good stuff that we did last week for reducing U-band data with them. But yeah, so this this LCOGT ingest script is how you want to ingest standard fields. And then I also have a note in the tutorial thing. So if when you ingest a target, so like I ingested a new target L94, so you should run compare catalogs. I'm not gonna do it right now because I don't have to, but you should do that. So that'll grab the catalogs, the relevant catalogs for this field. And then you also have to update the database like we did for L101 to make sure that the pipeline knows it's a standard field. And you also have to move its Landolt catalog to the right place.
Jamie, supposedly you could ingest science, like supernova images this way as well, instead of downloading from Snacks?
Yes. Although you have to be on the proposal, which I think not everyone is.
Ah, right. Okay.
I thought that is it just the proposal, or do you need some kind of Snacks access or supernova machine access?
It should be separate from the supernova
Okay.
machine and Snacks. So I think like if you're trying to ingest, you know, key project data, as long as you're on the key project in the LCO observation portal and the LCO archive, then I think you should be able to ingest stuff like that. Although I haven't tried that, so.
I do it regularly.
Okay, nice.
Yeah, you can do -P for proposal, and I still need the -- public for whatever reason, but yeah, it's possible.
So, but I guess if for anything that's more than a year old, it's public, right? So you don't need to be on the proposal. But I wonder if you try to download something new, if it'll let you do it.
You can give it a try and report back.
Okay.
Yeah, this is I know the LCOGT or LCOGT ingest is like in our cron tab on the Supernova machine. That's what's actually ingesting stuff onto the Supernova machine and then into Snex. So that's how we ingest all our data. So it's definitely doable.
Yeah, Stefano wrote ingest tar to allow external users to ingest data. So that was what that was explicitly written for.
Okay, cool. If there are no other questions and comments, then I'll move on to the next thing. So this is reducing another epoch of 17 CBV data, but this is more like how I actually reduce stuff, so I wanted to demonstrate it. This is in the batch reduction and upload section of the tutorial. So I'm actually gonna start this. So I'm editing a file called 17cbb_01.sh. And then I'm gonna copy the thing that I had posted in the tutorial into there. The only thing I need to change is this catalog name. So we'll do some bin magic to do that. Cool. Okay, so these are all the steps that we ran last week. We've got the PSF stage, the PSF mag stage, the ZCAD stage for both the Landolt and the Sloan filters, and then the magnitude stage for this new epoch, 2017-05-18. So we're just reducing that new epoch with all the same commands that we did last time. So I'm going to do shell or sh that. And then that'll start going. Cool. So this is how I usually reduce my data. I have these shell scripts and then I run them in sequence. So like my first pass through the data, I'll do, 17 CBV 01, then the second one will be 02. And this gives me a record of all the reduction steps that I've done, so that if I'm doing some difficult reduction and I have to do multiple passes through the data, then I have a record of what I have done. And if I want to revert to a previous step or a previous version of the reduction, it's easier to do that. So cool, that's going through, which is good. Just to give you an example of what this looks like. So this is me on the actual Supernova machine where all the data live and where I have usually reduced data. So these are all the objects of data that I've reduced. And if we go to one, this object, 19YVQ, the one that I just wrote a paper on, this had a very difficult reduction. There were lots of things to deal with. It's very close to its host galaxy. So there were a lot of steps that I had to do and redo. So the fact that I have like 30 shell scripts means that I tried to reduce it 30 different times. And so for each one, I will like adjust the full width half max or like try a different catalog or like use different, arguments. And so doing this in a batch version and with these shell scripts, like built up documentation of how I had reduced it. So it's easier to both redo in the future and, you know, see revert to older things. So yeah. So this will still take a minute, but it won't take nearly as long as the first round through the
Jimmy,
tutorial. Yeah.
can I ask a question?
Mhm.
So I usually have these shell scripts, but I rarely run them straight through because I want to like check the PSFs and make sure that I think the PSF looks good before I move on to the PSF mag stage. And then,
Mhm.
you know, if I get to difference imaging, I want to look at the difference images before I move on to the next stage. So do you just batch process everything, and like how do you handle those like special cases where you change something and like recording that for reproducibility?
Yeah, so I might have one script that just does the PSF stage and like does the same arguments for all the data, and then the check PSF is in the bash script, so I can see if those arguments actually worked or not. And then, you know, I might mark some of those as bad and then reduce the bad ones with another bash script with different arguments. So just trying to like actually keep track of the history of all the steps of reductions I've done. But yeah, this is definitely like in an idealized case where I already know all of the arguments that are going to work successfully. Yeah.
Ben, we're on the batch processing section.
Okay, so it's done with the PSF mag stage. Now it's going through the 0 points. First for the Landolt filters and now for the Sloan filters. Okay, cool. And so now this is my full light curve for this tutorial. So this first epoch are the ones that I had reduced beforehand. The second epoch are the ones that I just reduced now. So you can click through and see how those look. Cool. Press enter to get out of that. And so this section also talks about how to upload data. So Craig added this to the pipeline relatively recently. Whoops, let me do that. So this is the last step, which is the get mag step. I'm gonna say O for output. This is generally how you save files. So if I just do like O, then instead of bringing up that interactive plot, this would just output the light curve to this file. So this is what we do normally to send people data. But I'm going to do this extra step. So I'm going to do this. Other people can if you want to, but this is just to demonstrate how it works.
Are you on the right branch? No, it should be on master. Jamie, can you go to your pipeline and look at the log? Maybe like,
Oh God. Oh,
like
no.
get log -4 or something like that.
Did get log -4?
Yeah, that'll just give you the last 4 commits, and I want to see if this next 2 commit is in there.
Is this where I installed stuff? Okay, wait, let me.
I think you just need to update your pipeline.
Yeah, okay. Did I?
And maybe check what branch you're on.
Yeah.
Is this
Okay.
actually good to see how to do from within the Docker?
That's true.
Or do you need to reinstall the whole Docker? How does that work?
So I
So-
think I will need to exit the Docker and then pull the latest branch. Or pull the latest version. Okay, hold on. I don't know why all this random stuff is here. Let me.
So let me take a minute to say that like we're still actively developing this pipeline. And I've set up the pipeline channel so that things that I think you might care about show up there when we do it to the repository. So like when we merge something new into master, so when the pipeline gets updated, you can see, you know, what got updated there. Also, I think if someone opens a pull request, so if someone contributes something new, you can also see it there.
So what is the procedure for me as a user to, if I see something updated and I want to update the pipeline on my end, do I do it from within the Docker or do I repeat the whole, I download a new Docker?
I wouldn't download, what I think what you can do, and Jamie, tell me if you think I'm getting this wrong. I would exit the Docker, go to your lcogtsn pipe directory, type git pull origin master. That will get you the newest version. Jamie, I don't believe this because I just made a commit to the README
Yeah, let
this
me.
morning.
I think I accidentally built. Yeah, I think I built the pipeline from the wrong place.
Okay.
So
And so then I think you then need to build Docker again, but it should be pretty quick because Docker is really smart about only redoing the stuff that's changed. So like one of the things that takes forever in the Docker is IRAF, and I don't think it'll rebuild IRAF because it'll see that you haven't touched that. It'll just basically reinstall the pipeline.
Okay, so you do that. So you do that from outside Docker, and then you rebuild the Docker, and you should just do the differences. Okay.
correct. Yeah. So I'll do that git pull origin master. So this is just the minor thing that Asli updated.
And are you on the master branch?
Yes. Oh, God. What are you doing? Sorry. Okay. And then I'll build it. Good.
So that was a little installation you just saw there, and super fast because that's an easy thing.
Mm-hmm.
What did you run? You ran the git pull and then the.
Yeah, so I ran, first I ran the git pull origin
Okay.
master to get the most recent version. Here, I can write this in the.
Jamie, I can do it if you want to keep talking through things.
Okay, sure. So yeah, I did git pull origin master, and then I rebuilt the Docker image, so this Docker build command. And then the Docker compose command to start the database. Okay, ready for connections. Excuse me. And then the Docker exec command to actually start things. Okay. So all my data are still there. The database didn't get deleted or anything. Everything's fine. Cool. Nice. Perfect. Okay, so now I'm going to run this, upload this next to command. Okay, so this has some options so that you can label your data correctly. So it says the default photometry type for non-difference imaging is PSF. I'll just press enter. Please enter the group. I'm an LCO person. Is this reduction final? Yes. The list
The
data
group
used in
is
the paper.
free text column in the database.
So Craig, do you wanna talk about how this stuff is stored in next to?
Yeah, so most of this stuff is going to get written to a custom table that I wrote in this Next2 database. And basically, it keeps track of what I call data product extras. So things that are associated with these data products, like this CSV file that you're going to upload to this Next2. So it writes things like the group, if it's final, like reductions or not. If you do background subtraction, like the subtraction algorithm that's used and things like that. So really all this does is that when you go to Next2 and you go to the photometry plot, you can select different options. So for example, you can select the options, like select different groups that upload photometry. So you can only see groups, or you can only see data from like LCO, for example. So if you like mess up any of this, the only thing that's going to happen is that that's going to get added as like an incorrect option in the database. So it'll show up on like the photometry plots. So it's sort of easy to fix for one of us. But yeah, I guess try not to mess this up if you can. That's, easier said than done, I know.
Thanks. And I can upload multiple versions of photometry, or?
Yeah, so each of these will just get written to and uploaded as its own file. So you can yeah, depending on which parameters you know, enter in here, you can, you know, on the Snex2 page, select different options and only see the, you know, the photometry files that match those parameters. So it asks, you know, one of these asks if the reduction is final or not. And hopefully that'll only be uploaded, you know, once. But otherwise, you know, if you want to experiment with, you know, PSF versus aperture photometry, different subtraction algorithms when you use, you know, background subtraction and stuff like that, that's sort of a way of keeping track of these different versions.
Thanks.
Thank you for explaining that, Craig. So we can keep going through these options. So is it going to be used in a paper? It's not. And then Craig has just imported all of the Snex users. So you should have a account on Snex2 with your same login credentials as for Snex1. Upload successful. Cool. So now I'll go over to Snex2. Snex2 is at test.supernova.exchange. We're still in the process of polishing it and also fixing some bugs and adding some things. So this is not final, but this is hopefully what we plan to use going forward. So this was data for 17 CBV. So here's what its page looks like on Snex2. If we go over to manage data, you can see here's the data file that I just uploaded, 17 CBV tutorial. And then if you go down, this is the photometry plot, and there are a lot of options down here. I had final reduction, so these are my final reduction points that I just uploaded that you can now look at and do stuff with. If I just want to go back to like the full normal light curve, then there's the normal light curve. Yeah. So this is how we are planning on doing more version control of photometry in the future, and also how we're planning on getting external people like to upload their photometry into our database more. Okay, sweet. So great, that's the end of that section. The next thing we're going to do is the subtraction section. This has a few steps that take a long time, so I'm going to get started on that. So I'm in my data reduction directory, and the object with images that we'll use for subtraction is 18cow. So I already have an 18cow directory. If you don't have one, I suggest making one. I'm going to copy this.
And this is, I want to just reiterate again that it's really useful to do each reduction in its own directory, because the pipeline creates temporary and auxiliary files, and you just don't want those all mixing with each other.
Yes, a very important thing to reiterate. Okay, so for 18cow, I just gave it a broad date range, and you can see there are two epochs of data here. One of them is on 2018-07-01. It's this first set of images. and then one of them is much later, 2019 0831. So these ones in 2019 are the templates. Subtraction has a couple extra steps. So actually this first one is not critical, but the pipeline expects these template observations to already have PSFs before you start doing anything with them. So I'm just gonna create some PSFs to start, even though we're gonna overwrite those pretty quickly.
What do you mean we're going to overwrite them?
One of the steps is marking things as template observations, which are stored separately in the database. And so we're going to make PSFs more carefully for those images after they get marked as templates.
Got it.
Yeah.
So this is where we haven't really talked about different file types yet, but everything we've been working with in the default is file type 1. File type 2 is merge, and I'm pretty sure that's broken, so you'll never see file type 2. File type 3 is difference image, and file type 4 is template. So when we start using these different file type flags, that's what we're referring to. 1 is just kind of normal standard processing, 3 is difference, 4 is template.
Cool, thank you for saying that. So I'm gonna open up a DS9 window because this next step requires DS9. So if I look at this is the template where this is the epic where the template images are. You can see I've picked out 3 images, one for each filter, G, R, and I. Typically, we request multiple observations per filter. So if you have an epic of template images, you'll want to go through and pick out which of the 2 images per filter is better. Maybe one has a satellite in it and you want to ignore that one or whatever, but I have pre-selected the good ones for you.
Jamie, can I ask you what you use for visualization of the templates? Like which command? Or if you just open it in DS9?
Honestly, I usually just open it in DS9. So like, this might get confused with multiple DS9 windows, but yeah. So there are ways to open up the images in the pipeline, like the check PSF stage and the check WCS stage opens them up. But that usually like marks stuff on the image. So I can just open things straight in DS9 to look around and judge them. So this actually isn't a perfect case. It has this weird thing on the bottom, but it doesn't have any satellites. So I'm gonna ignore that. I'm gonna close my DS9s since I have multiple of them, and that can confuse it, and then reopen one of them. One way to select images is with this D flag. So D is short for ID number. Each of these images has an ID number, like 87, 89, 91. So I'm going to select that image by ID number and then run this template stage. So that'll mark it as a template. And then I'll redo that with the other two images as well. So the other two ID numbers. Okay, cool. So now this is what Ashley was saying with the different file types. So now I'm looking at the same epic, but I'm adding this flag for file type 4. So like Ashley just said, 4 is for template images. So you can see here are my images that have now marked as templates. They've got this temp thing in their file name, which is short for template, not temporary. When you're running difference imaging, you have to run cosmic ray rejection. So I'm going to do that. This really makes my computer freak out. So if you hear a loud fan whirring, don't worry.
The cosmic ray rejection is multi-threaded and it tries to be intelligent, but there is a flag that you can tell it to use fewer processes if you would like.
Yeah, I think it's --n cores.
I could look it up. I always guess wrong. -- multi-core.
Multi-core.
This is another thing that I messed up when I first started running this. So there's this multi-core option and it's implemented for some, but not all of the stages. But the recommendation that I've received is that it's better to run parallel shell sessions, like on different filters in different directories, than to run everything with this multi-core, trying to be smart about where you want to multi-core in different places. Jimmy, is that your policy as well?
Yeah, I think the only stage that we reliably multi-core is this cosmic ray stage. All the other stages, the way they interact with the database and then also the way they generate auxiliary files does not make them very multi-threadable.
So as you'd open you'd do a new Docker exec from a different terminal window, or how would you do that in Docker?
I don't use Docker because I'm doing everything on Dark where Stefano installed the pipeline. I think that that's right. Jimmy,
Yeah,
do you know?
I am pretty sure that's what to do. So let me.
So if you open a new Docker in a separate window, they talk to the same database.
Yeah, correct. They talk to the same database and they have access to the same data. Yeah.
Because it's the same container that each is looking in.
Okay.
And I usually do it by filter just to keep my brain straight. So in my 2018 COW, I have like a B band, V band, G band directory, and then I run those the commands for those filters in those directories.
Okay, cool. So I'm going to copy the next command in here. This is the getting the templates. So with file type 4, running the PSF stage with some extra arguments.
Jim, can you talk about those extra arguments, like how you chose them?
Yes.
Why are they your defaults?
Yes. So I chose the datamax argument because there are some bright stars in the image, so I want to make sure that those are excluded. I chose the nstars argument because I want to make sure that I often do nstars 12 instead of the default of 6. just to make sure I'm averaging out more stuff. And then this, you can also set full with half maxes of your PSFs. This is slightly smaller than usual. Usually it's more like 5 or 7 if I set it manually. But in this, for these images, one of the stars I was picking had another source very close to it, and so if the full with half max was too big, then there was this extra like lump in the PSF that I tried to exclude by making the full with half max smaller. Yeah, and then for these templates, especially, you should make these PSFs very carefully. So I'm doing it with show, so that I can look at each PSF individually. So that one looked good. It was nice and symmetric, didn't have any weird things. Because these template PSFs will affect every subtraction that you do. In this case, it's not very dire because we're only reducing 1 epoch, but if you're reducing 100 epochs and these PSFs will affect all of those subtractions, then you should make sure that they're extra good. So that also looks nice and symmetric, and the image looks pretty clean. And so this again, this is the I-band image. So if people haven't looked at data very much, this weird background pattern, like splotchy thing, this is just called fringing, and this is very typical for I-band data. So that's not surprising, looks pretty normal. And this PSF again looks nice and symmetric. I'm gonna double check that those got generated correctly. And they all have PSF files. Good. Okay, so just copying the next step is to run the cosmic ray on this earlier epoch in 2018 is our science epoch. So I'm running the cosmic ray stage on the science images now. This will take a minute. This will take 3 minutes because I don't have enough cores in the Docker container to do all of them at once. So I'll have to do it in 2 stages or in 2 sets.
Do people have any questions? What has been covered so far?
So the image you showed, what's that? You know, on the background had some patterns like
Yeah, so this is called
issues or something, some problems.
Yeah, so this is the pattern is called fringing, and it's I know it's common in our I-band data. I think it has to do with when the wavelength is comparable to the thickness of the silicon in the chip, and it makes photons like bounce around in it a little bit and like scatter through it.
Yeah, it's an internal reflection. And it's basically you get the redder photons. Yeah, that's exactly right. They reflect, and so this is just a dispersion pattern.
Oh, so those cannot be corrected by flat.
That's right, because the flat field has a different illumination, and so because it's a diffraction pattern, it's pretty sensitive to changes. And so there are ways we can correct for it by taking all of the I-band data across all the night and things like that, but we haven't implemented that. Generally, while it looks bad in the background, it doesn't affect the photometry enough that it's been a problem big enough to fix.
Okay, thank you.
But yeah, that is a good point. If you see this pattern in IBAN data, it might look very weird and like your data is messed up, but it's really not not anything to worry about. Okay, cool. So that finished running. My computer's fan is now getting a workout. So now all our science images have also been cosmic ray rejected. So I'll run this next command, which is basically similar. It's identical to the one that I did before, but now on the science epic. And I guess I also added this max apercore thing that Azalee mentioned last time to make sure that the PSFs get saved and generated correctly.
Need that? So my personal feeling is that if you have to set max apercore, something's going wrong in your PSF stage, and you should look at it more carefully. Because it's saying that the aperture photometry doesn't match your PSF photometry on average for the stars in your catalog by more than 0.1 mag. So right now you're allowing that average mismatch to be a full magnitude.
You're right. When you put it like that, probably not ethically the right thing to do. I haven't had to troubleshoot things when the aperture correction is large. Can you talk about some of the steps you do or things that you check?
So I think that we isolated it in almost every case to it being an issue with the first star that was selected as a PSF star, and that being too bright a star, and it was messing with the normalization. So what I do is I usually mess with data max and just dial it down. I look at what stars were selected and what that Dmax value is, and then I dial it down a little bit until it comes into alignment, and that fixes it for almost everything.
Okay. That is good to know. I'm wondering in this case if it's also because, one of the arguments I put was that the full with half max thing, so setting it more small so to exclude nearby source.
So like how confident are you that that's really makes it used or makes it like that overwrites the pipeline itself? Because like if you scroll down to where it like no, up a little bit, just a little bit. Oh no, okay, it is hard coding the full with half max to 4. Okay, never mind. I kept trying to modify that, but maybe, and it like never made a difference on my PSFs, but maybe I wasn't using it correctly. I think I was trying to choose different stars with that, not like eliminate secondary sources.
Yeah, it should definitely affect your like the plots that it displays. The PSF should definitely look like the area that those cover should depend on the full with half max. Okay, so I'm gonna start this next command, which is the command that actually runs the difference imaging, because this will take a while. Okay, so to talk through this command, so I'm picking out the science epic. Ultimately, I'm running the difference stage, and then there are several arguments in between. So this first one, this normalize argument, you can decide whether to normalize things to the template images, which is what T is for, or to the science images, which I think is I.
And this is normalizing the 0 point.
Yes.
Right?
Yeah. So I typically do the template images, although I have had issues if I use Sloan templates, then that can confuse things. Then I have to normalize things to the images. But when I have LCO templates, I usually normalize to the templates. This next argument, this dash capital T, this is T is short for telescope, and so this is picking out which telescope your science images you're selecting are. So in this case, I'm selecting FL. So FL is the instrument that's on the 1 meter telescopes. And then I'm specifying when the temp date is. So this is the second epoch when all my when my templates were 2019 0831. You also have to specify the telescope for the templates. In this case, it's slightly confusing because LCO updated the cameras that are on our 1 meters, and so the file names were renamed from FL to FA. But it's the same telescope. It's just a slightly updated camera on it. So all our recent data have all our recent 1 meter data have FA in the file names, and stuff from like pre 2019 have FL.
Yeah, so really what happened was it's the same silicon, but we upgraded the controller. And so we went from these LCO developed controllers to the Archon controllers, which are developed by STA. And so, but the silicon is exactly the same.
Yeah, so it might look like I'm selecting different things because one of them is FL and the other's FA, but like really it's almost identical. This next argument here is diff type. So we have 2 different algorithms that we can use to do subtraction. So 0 does hot pants subtraction, and 1 does Pi-Zogi subtraction. Pi-Zogi is another algorithm. I typically do Pi-Zogi subtraction, but hot pants is much quicker. It's still slow, but it's quicker. So I'm using hot pants just to demonstrate it. This fixpix is an argument that is only applicable to hot pants. Not 100% sure what it does, but
It calls IRAF fixpix. That's not run with Pi-Zogi because it's done before hot pants is ever called.
it is. Okay, then maybe it is used in both of them. Interesting. And then the last argument is just specifying that this is the difference stage. Okay, so this outputs a lot of stuff to the screen. Yeah, I ignore most of this unless there are obvious errors. When things are nice, it prints a big success, so that's good. And then it tells you it's inserting all this stuff into the database. So this is the new database entry for the successfully subtracted image. So yeah, this will definitely take a few minutes to run, even though we're just doing 6 science images.
So this is something that like I'd definitely be curious if you decide you want to like play with Pi-Zogi versus hot pants. My experience is that Paizogi does a much better job like smoothing out the background. It takes longer and it also errors out more frequently. And so like it doesn't necessarily process everything. And I actually today plan on looking into that a little bit further about what images is it erroring on, and is that something that is worth fixing somewhere, or is it erroring for good reason? But that's just, if you're playing around with that, I'd be really interested in your feedback on what your experience is with the different imaging algorithms.
Oh, there was one other thing I wanted to say. So this is typically like if I'm doing a full objects data set that I'm running subtraction on, this is typically something that I'll start running in the afternoon in a shell script, and then I'll just leave it running overnight, and then it'll usually be done by the time I get back into the office in the morning. Especially if I'm doing Paizogi, then it can take multiple minutes per image, so it can definitely take several hours if you're doing a full images data set. So I'll just leave it running overnight.
So also, if you're using hot pants, I guess while we're waiting, the two flags that I play around with if something doesn't look good is there's a convolve flag, which hot pants chooses whether to convolve the template to the image PSF or the image PSF to the template PSF. It generally does a good job. Occasionally it doesn't. And so the convolve keyword, you can pass it again, the T or the I, like you can the normalization, and force it to choose one way or the other. And it's like convol 00 header keyword, which tells you which it used. And so you can look at the image, figure out what it used, and use the other one. The other one is the background order. It's set to be 3, and the flag for that is BGO for background order. I have been finding that 3 is often too large, and I end up with a large gradient in my background that I don't see in either my science image or my template. And so sometimes I set that to 2 or 1. And so those are the 2 flags that I play around with for hot pants. For Paizogi, sometimes if you have a really sparse field, you get an error about not having enough stars. And for that, you can use the unmask flag, which doesn't mask the cosmic rays. And so this can happen if you have a cosmic ray flagged near like one of your 5 PSF stars. Paizogi is going to look at the PSF region around that cosmic ray and mask that. And then if that overlaps with the PSF of your star, that star gets eliminated. So this is mostly an issue for sparse fields. You don't in general want to ignore your cosmic ray mask, but that is an option if you're getting that like not enough sources found error. Curtis, do you want to just say what editors are installed in the Docker container or editor?
Yeah, I think VI is the only thing that's installed natively. If that becomes a major problem, we can add to it, but yeah. Right now, by default, that's the only thing that's installed. Docker containers are meant to be very, very bare bones. So
So it's nice to have this, statement what's doing, but when you make sure you run successfully and then want to do large batch job, you could turn off this kind of comment, could save CPU and running time. I don't know, maybe too much work to do. I wonder, is there any a convenient way to do that?
I think that the slowness is computational. It can be annoying having everything printed.
No, it's not annoying, but could save, CPU running time. I wonder.
Yeah, I don't know if that's an option in Hot Pants, but it's definitely not implemented in the pipeline.
Okay.
yeah,
So
you don't lose a lot of CPU time to it, especially if you pipe it to a file. It's pretty minimal overhead, so it doesn't slow things down dramatically. If you are doing a large batch job, I generally recommend piping stuff to a file rather than just having it print a screen though.
Okay.
Okay, cool. So it has finished running for me. So I'm gonna go back and this is the science epic, but now we want to pick the differenced images. So like Leslie said, those are file type 3. So here are my 6 differenced images. You can see they have diff in the image name now.
it's always nice to also specify the diff type to be safe. Both will show up if you have both available and you don't do that.
That's true. So let me do, so yeah, you can pick out difference images by diff type as well. So I did diff type 0. Yeah. Okay, so now my DS9, I closed it for some reason, so I'm going to reopen that up. And then this is the next command that's in the tutorial, is this check diff stage. So that lets you look at your difference images. Okay, so I'm going to do frame, tile, and then that opens up all 3. And then I'm also going to go up here, frame, lock, frame, image, and now they're all locked together. Okay, so this top left is the science image that we started with. This top right is the template image. And then the bottom here is the subtracted image. So, whoops. So you can see this is the host galaxy. In the science image, you can see that 18 cows clearly there, but it's obviously getting contaminated by the galaxy. In the subtracted image, 18 cow is the only bright spot that's left over, and there's no obvious weird stuff going on with galaxy subtraction, so that looks good to me. You can zoom out. The other sources are also gone. There's like a little bit of artifacts left over, especially on the bright stars. It didn't do so hot on those, but that's pretty typical. So this is a pretty typical subtraction, I would say. Some artifacts on bright stars, but sorry, my mouse is getting confused, but the source is like very clearly the only real source left in the image. So here again, you have some options. If you just press enter, it'll say it's a good difference image. If you press no, it'll delete the differenced image, so you have to redo the different stage. Or you can mark everything as bad, and you shouldn't do that very often. So just looking through all these, again, 18 cows clear in each of them. And then you can also zoom out and look at the zoom out thing up here to see if there's anything else weird going on. But these are all looking like pretty good subtractions.
So where do you get those catalog images?
Sorry, where do we get the what?
The second image you showed. What?
So this is the template image that we set.
Mm-hmm.
And so it has picked out the template image for the filter, and then that's what it's displaying up here.
So those template images you accumulated over the time using the same instrument, is it?
Yeah, so in this case, we had template images that were taken later by LCO. We try to use LCO templates whenever we can. There's a separate thing, and it's detailed in the Authoria documentation that's specifically for difference imaging, where you can ingest Sloan templates, but you can only use those on GRI. And yeah, I try to use LCO template images whenever possible.
And you can request a template if it's been long enough. You know, if you think your source has faded and you need a template, you can always put in a request in Snacks for the template. And it's nice to have a little comment that says, I'm getting templates, so that LCO people know what you're doing and can improve it easily.
Yes, yeah.
Right, but I mean, the problem is you have to wait until the supernova are fainted.
Yes, that's true.
So is there a way we can accumulate this template in nearby galaxies?
That's not part of the program.
I think, Yair, did you try to do that? Did you try to have like a background program that just got template images, but then that like crashed the scheduler or something?
Yes, so we wanted to have a program that just, give it a list of 1,000 nearby galaxies, and whenever there's a gap in the schedule, just have LCO take an image. But the solver in the scheduler at LCO tries to solve everything simultaneously. So when it has 1,000 more targets than we'd give it a window of the whole semester. So there's a ton of options of where it could schedule them, and it crashed after we submitted about 200. So I had requested that there'd be the secondary scheduling step where it schedules normally and then it tries to fill in the gaps with some background program, but I don't think that's been implemented.
Maybe
Yeah,
a
that's
1,000 is too many, maybe step by step, you know, like 100.
Yeah, but even with a few hundred, giving it the full semester window, just trying to say, you know, observe this whenever you can, it increases the complication of the solution, the complexity of the solution.
Yeah, it does. And actually, there has, believe it or not, been a little bit of movement on that in the background, which is great. So there's been a couple of things that have happened. One of which is they've been doing quite a few optimizations on the scheduler just so that it can handle more observations in exactly as you described. So it actually might be worth reaching out to Lisa again and seeing if we could try our experiment again with some of these new optimizations. The secondary part that's happening is we got some funding to open source our schedule. They're going to be building a scheduler simulator, you know, things like we've been asking for a long time. So that's hopefully going to be really good.
Okay. If anything, we can, you know, contribute as our voice heard, then let us know.
Yeah, thank you. Okay, so I'm gonna keep going on with this. This last one, it looks like there's some weird like fuzziness in the background. So this makes me a little suspicious, but we'll keep going on.
Jamie, what do you mean by you mean like there's just extra texture,
Yeah, they're like
like beyond the I-band fringing?
yes. Yeah, I don't know what to say besides it doesn't look the way it normally does. But it also doesn't look insane. Like there's still the clear 18 cows, the clear source, and most of all the other sources have been subtracted out. So it looks a little weird to me, but not insane. Okay, so I think there's a step that I actually skipped. So, oops. Cool. So I will write this into the tutorial, but you do have to run the PSF stage on your different images. This should run very quickly. It's just copying the PSF into the right place. But
It takes a little bit longer for PyZogi there. It's actually making fake PSF images for the PyZogi PSF.
True.
But for Hot Pants, it's literally copying over. It looks at the convolve keyword and either just copies over the template or the image PSF.
So I will copy this command into the tutorial for completeness. Okay, cool. And so now after I ran the stage, I'm just pulling up the images again, and so you can see they all have the PSF keywords correctly in there. So that's good. After the PSF stage is the PSF mag stage, and the PSF mag has these extra arguments, X and Y. And so these set the order of the background that is trying to fit around the supernova. By default, these are 3. For difference images, the background should be flat. So I'm just setting the background order to 1 for each of those. And then for each of these steps, just like the same thing with the first basic reduction we did, you can also run the check PSF and check mag stage after you generate the PSFs and do the PSF magnitudes.
Let me say something about that.
Yeah.
Which is that so this aperture correction is a correction that is applied to the PSF magnitudes based on the aperture photometry of the catalog stars. That gets complicated when you're convolving things, especially with piezogi, which doesn't use either the image or the template PSF, but does its own PSF. And if you're doing that on a difference image, the aperture correction doesn't necessarily translate straight through to difference imaging. So because of that complications and ambiguity and potentially applying different corrections depending on which difference imaging you're using and with varying degrees of scientific correctness, we set the default fit type for difference imaging to be aperture photometry. So that means that if you run the mag stage and you don't specify which type you want it to put in there, it's going to put the aperture photometry in there for difference imaging, but the PSF photometry in there for not difference imaging. And that's just something to be aware of. I've also empirically found that aperture photometry, even on difference images, tends to have a bit more scatter in it. Theoretically, it shouldn't, and I don't know why, but that's just something that I've found and to be aware of. This is another one of those things where like you can use the defaults and the defaults are sent to be the most scientifically safe. But if you want to be really sure about what you're doing, then specify the -- type keyword.
Cool.
I'm sorry, at the mag stage, just at the mag stage. And the ZCAT stage, the ZCAT and the mag stage.
So you are saying the default is the aperture photometry. If we want PSF, we have to specify. Is that what you mean?
Yeah. So the PSF mag stage produces instrumental magnitudes for both PSF photometry and aperture photometry, and those go into different columns in the database. So at that stage, you're doing both, and it doesn't matter. Where it matters is the ZCAT stage has to look at one of those columns and the mag to produce a 0 point. And then the mag stage has to look at the one of those columns to produce an apparent magnitude. So for difference imaging, it looks at the aperture photometry. For not difference imaging, it looks at the PSF photometry by default. But that there's a flag, the -- type flag, that allows you to explicitly set which one you want it to look at. And that you can do that no matter what to do whatever you want to do. This is just what it's set to by default if you don't specify the type.
Okay, so probably, you know, some residuals from the difference somehow, you know, around the supernovae, so that contribute a little, you know, uncertainty in aperture photometry.
Yeah, I agree.
Cosmic rays or
It's just scientifically the most conservative, most correct thing to do. And that's why we implemented it as the default. There wasn't a clear right way to deal with the aperture correction with PSF photometry in the difference images.
okay.
Okay, so after you do the PSF mag stage, you do the ZCAT stage. So we'll do that next. So in this case, 18 cow is in the Sloan field. So, oops, where'd my command go? So I'm specifying -- field Sloan. I only have Sloan filters in this case, but I'll specify them to be consistent. And then this might be a disastrous thing to ask, but Esley, in this case, they all have PSF mags, but not aperture mags.
So that often is solved by setting data min and data max. If you're watching the PSF mag scroll through, you can see that the aperture, it has trouble with the aperture mags. I think this will lead to just having no mags.
Yeah,
unless you
so,
specified the type. So yeah, by setting data min and data max fixes this.
Okay.
And I think that's suggested in the Authoria document.
Okay.
And it seems to happen like much more commonly with difference imaging than non-difference imaging.
And so that's, so do you have to redo like the PSFs and the
Just the
subtraction, or
PSF
just
mag
the
stage.
Okay.
Yeah.
Interesting.
I suspect it has to do, I have no idea. I'm totally making up guessing here, but my guess was that it had to do with having your background fluctuating around 0 at some point. It might mess things up. Because yeah, I see it with difference imaging much more often.
Okay, interesting. Let's not do that just to show. So now I'm doing the last step, which is the magnitudes. And in this case, like Esley said, the correct thing to do is to rerun parts so that the aperture magnitudes are not broken. But I'm gonna be super lazy and just specify that we're using PSF magnitudes, even though you should use aperture magnitudes for subtraction. So that's that type fit type keyword that she had mentioned. And so now I have magnitudes. And now I can run the get mag stage. And so, cool, now I have my light curve. If you click on a point for normal imaging, it'll just show you what the PSF extraction looks like, but for differenced imaging, it'll also show you what the differenced stage looks like. So you can see both of them at the same time. You can click through and see. It takes a little bit longer to load because it's loading the images instead of just the stamps as well. Here's what, so that everything is looking normal. Different filters are within 1 sigma of each other. These last two are a little bit offset, which makes me a little nervous. And this last one, this stamp looks weird. So here's what the normal one looks like and what the noise looks like for all the other ones. This is pretty typical, but then this one that's offset, the noise pattern looks kind of weird. So I would delete this point and then try to mess with some of the parameters to redo the subtraction. But yeah, this is how you do difference imaging. So it does take quite a bit longer, especially with the actual difference step. Iterating on that can be can just take some time. But you're doing basically all the same steps as normal reductions. You just have to pick out the templates and then do cosmic ray subtractions and then the difference step. But yeah, I think we are done. So I'll stop sharing. Are there any questions?
So these difference magnitudes are uploaded to SNEX2 in the same way?
Sorry, can you ask that again?
The difference magnitudes, you can upload them to SNEX2 in the same way. There's no difference.
Correct, yeah. I think Craig, I think there's an extra step that'll ask you what algorithm you used.
Mm.
But yes, you can upload those as well.
Yeah, and it intelligently sets the defaults in terms of the file type, and it knows that the default is aperture photometry and stuff like that. I did want to say, when I was talking about processing everything with different filters, that's only through the ZCAT stage. The ZCAT stage needs to be processed with multiple filters. So at that point, I start joining at least the Sloan and the Landolt filters, if not everything all together in processing.
All right. Well, if there aren't any other questions, thank you all for coming. Please continue to ask any questions you have about the pipeline in the pipeline channel, and we'll try to help out as much as we can.
And yeah, I mean, definitely read through these documents, read through the manual. There's a lot of information in there. And like I said, if there's stuff that needs to be updated, let us know, or even better, update it and contribute to the repository.
Thank you very much. It was great.
Sweet. Good
I
to
will
hear.
also say it is unlikely that we will implement feature requests, but bug fixes we definitely care about. And yeah, thanks, Jamie. This has been great.
Thank you.
Thank you for all your help.
Okay, bye.
All right. Bye, everybody.